nanohub.org.
Online simulation and more for nanotechnology.
All right. Good afternoon. So this would be the last class of this course. And although this was just a 5-week-long course, we have actually covered quite a bit of material. And what I'd like to do in this last lecture is to remind you the topics that we have covered and the key ideas that I wanted to emphasize. And I hope when you study the material together, you will remember the big picture, which is always the important thing when you're learning a new material. So let me begin by reminding you that the topics we covered, I emphasized from the very beginning that the data that we talk about is often the output of some process, and this could be gate dielectric breakdown, the time when the dielectrics break, or it could be the number of clicks in a web browser. So these are the sort of things that we see on output of an experiment. And X are the variables that lead to this. For example, for gate dielectric breakdown problem, these would be the voltage that you apply across the oxide, or the temperature across the oxide, and so on and so forth. And often our goal has been to find out the function that connects the input to the output. So in the first 2 lectures of the semester, I tried to explain to you why one should really pay particular attention in understanding the data and treat the data with respect. And then even when you have to throw away data assuming that it's an outlier, there should be a methodology of how you identify them and never remove them from the picture completely, because that outlier, what we're thinking about outlier, may be down the road from some one physics reason or other, maybe the most important thing. So, but for the time being, having a good way to analyze the data, output data in a clean way without fitting or anything, that would be the first thing we did in the beginning of the semester. Next, what we asked that there may be a different way the output is connected to the input. The voltage and current, voltage and temperature may lead to oxide breakdown, but you may be thinking that this happens in a particular way, a particular physics way. Your friend may be thinking that there is no, that's not how it happens. It happens slightly differently. So that's the question. F is the hypothesis. And when you have multiple hypotheses, then what you want to do is to know that which one is reasonable. So that was our lecture 3 to 5. Then we sort of switch gear and we explained that when you are trying to calculate this F, or trying to determine the hypothesis in this lecture, it will work very well, or it will work better if you did the input variable, the voltage and temperature, for example, in a specific way. For example, if something varies as a logarithmic in time, and if you sample the whole thing in linear in time, that's not going to give you a very good Y, and you'll not be able to sort of test the hypothesis very well. So how to design the experiments, how to think about the X1, X2, the various input variables in a way that you get a set of Y that gives the maximum possibility of determining the function F was something that we discussed in detail. And finally, when the data is given large data set where you cannot really control X, for example, in that case, we use machine learning algorithms and these lectures to understand how do you do it statistically and what are the dangers and pitfalls thereof. So this was the big picture, and then these lectures in detail were arranged in this particular way. So what I'm going to do today is just go over the various lectures in brief, reminding you what the key points were. So in lecture 1 and 2, what I wanted to explain was where do data come from? What is the importance of small and big data? And I emphasized in the very beginning, of course, the original data is all written in our DNA. Our DNA is really a book that transfers the information without the need of any pencil on paper. Biologically, it transfers information from one generation to next for millions and millions of years. So that was the original form of data that we don't see, but is present nonetheless. And then there are, of course, archaeological data, which sort of is carrying this information about what this specific organism was, but it is being carried in its imprint through mud and in natural resources. Nobody, of course, wrote it, but within it, if you know how to read these things carefully, you will get a wealth of data from a time when the humans were not around. Then once the human beings started to learn how to draw, they began to sort of provide information, write information in a pictorial form. The pictorial form then eventually evolved into alphabet and languages and all. And so these were all carrying information from one generation to the next. And finally, scientific information. I explained to you the Galileo's experiments where he was dropping balls from a certain height and measuring how far they move depending on the velocity of the balls were thrown at, and thereby these notebooks then carry the information. Now, in one sense, you can say that these are small data because this involves only a few points. And language, well, how many letters does even a largest novel have? So it's not in that sense very big data. But then this is what I explained, that the very big data started when both the computers came along to process the data, but more importantly, when the memory technology, solid state memory technology, allowed us to save the data in a form that we can analyze later on. So this was a very important thing. In lecture 1, I wanted to emphasize the origin of the data as an all-encompassing feature about how we communicate our experiences from one generation to the next, or how we understand the world around us in a systematic way. Another way I explained the distinction is how Galileo, for example, once again, was looking at the moons of the Saturn and I'm sorry, the rings of Saturn. In the beginning, of course, he couldn't. His telescopes were not very powerful, but he was able to sort of see what looks like an satellite. But it later on turned out that this really a ring. And these days, of course, we know the rings in great detail because we have been able to send camera and space probes into this region. But what I want to tell you, although these data might look small, it is not small in its impact, because this is the first time then people begin to understand that the Earth may not be the center of the universe, but it may be turning around it. So what I want to say, the data may be small, but the mind behind it is not. The mind behind it is pretty big, and in that case, even a small data can do deep analysis, deep insights about the working of the world. Now, of course, these days we have much more data, and in here there's no Galileo sort of is observing it, but here one has to be able to sort of ask deep questions based on what is available to say deep things about what this data is trying to tell us in terms of the universe. So small and big data both are important. This is a factor. This is something I emphasized repeatedly. Now, once you have the data, whether it can come from this camera or it can come from the written document, maybe a novel or Harry Potter or something. You can then collect the letters, for example, or words example, and analyze them. So that's what I'm going to talk about now. Now, in doing this analysis, it's very important that we do not manipulate the data in any way. Don't touch the data. That's my emphasis. And this is something before 1920 people didn't understand. They always wanted to calculate an average. They always wanted to calculate a standard deviation. But the second you touch the data, you lose the story the original data is trying to tell you. And then therefore, from 1920s onward, there is this movement where this movement is called exploratory data analysis. And in exploratory data analysis, they focused on the discrete data itself. They didn't want to manipulate the data before the data had the time to tell the story. And for example, in this case, you have a bunch of data I explained, and in that case, we try to get the median. And the median is very powerful because you see, you can have 1 or 2 points which you may have mismeasured, and yet the median doesn't really care. Median is resistant to small errors that you can make. And similarly, instead of thinking about a standard deviation, I explained to you the interquartile range, which is the first quartile difference between first quartile and the third quartile. And then I also explained to you before in that lecture is that when you do 1.5 times interquartile range, remember interquartile range is Q1 to Q3, you should take these two ends and all the data that are within, that's what we analyze. And all the data that are outside, that need not be a part of your analysis. The reason is most likely when the data is so far out, then this is a separate class, and this separate class may be trying to tell a different story compared to the main thing. So we will keep the data when we plot it in a paper, or don't ever throw this data out. It is an outlier, but doesn't mean it's wrong. And then what we do is keep rest of the data in and analyze the data. This is what one thing I emphasize. Second thing I emphasize is never draw a histogram. Histogram is well-known for destroying the essence of the data, because you can give an histogram any shape that you want depending on the width of the legs of the histogram, because it just combines it. And so one thing this type of new types of histogram does is called a stem and leaf diagram. And the stem and leaf diagram, of course, has been explained in detail, but the point is the way you do it is that, let's say you have a bunch of points between 44 and 106, and what you do, there is a way to determine what the stem should be. For example, stem here is 4, 40, 50, 60, 70, 80, 90, and 100. I explained why is it in step of 10, not necessarily in the steps of 100. So it can be 100 depending on the data that you have. I gave you the algorithm, and then when you have 44, you put that blue point, 6 and things. This immediately tells you that there are four points in that histogram, and then there are 5 points in between 60 and 70 and so on and so forth. What is the bottom line? The bottom line is that although it tells you the frequency of the data, it has not really removed the data, original data. You can construct it at any point you like. So turn it 90 degrees and this becomes a histogram. So that was another point I wanted to emphasize. Don't touch the data by a processing program unless you know what this is all about. And I explained the algorithm about how this histograms are done. The point I want to make that in modern computers are so powerful that actually all these things are done all these things are done in the program itself. So for example, if you look at Wolfram Alpha, just put all this data in, it will automatically put it in the right bin, right size bin, and then that is what you should be analyzing it. Don't do it on your own. Then I explained to you how to draw straight lines. How do we draw straight lines when you go to school or high school? Then we learned how to draw straight lines. How do we do that? Let's say you have 9 points, and then we call a program in Excel or in program in MATLAB, and then we just feed the data. But this is dangerous because let's say one of the data point is somewhere, accidentally is somewhere here because we made a mistake in measuring it. And as soon as you do that, the single mistake will completely rotate the straight line in a different direction. Dangerous because you are allowing a single mistake to sort of bias your entire information. So what do you have to do? What you have to do is that if you have a straight line, we know that 3 points makes a straight line. So then what you do, you take the data, group them into 3, and then take a median of the x of these 3 points. Let's say it doesn't have to be 3. I mean, if there are 15 points, it could be 5, 5, 5. And then you take the 5 points, take their x median and y median, get 1 point. Similarly, in here, x, y median and x, y median here, and draw the straight line based on that. What about if you want a quadratic line to fit this? So then what you do is essentially group because you need in that case 4 points, right? 4 points in order to have a quadratic or a parabola. In that case, what you do is group them into 4 subsegments, and then use that median based approach to get the points, and then fit the median points. And the great strength of this type of approach is that small variation of these data points here and there is not going to be completely fundamentally change the main story that these data are trying to tell you. So this is something I emphasize repeatedly. Exploratory data analysis, where you respect the data as is something that is very important to think about. Next, I explain to you the importance of using the data which is imperfect. And in that case, for example, I explained that let's say you had 5 gate oxides, and you were testing them all in some way with some voltage. But what happened that you went over the weekend, and one of the probes that was sort of stressing the oxide accidentally got detached. Now, when you are trying to get the lifetime of those oxides, you see, up to that point, when the probe got detached, actually the oxide survived just fine. And so therefore, it is trying to tell you, although it did not fail up to that time, and you're interested in failure time, that by surviving up to the last point, how do you account for this information? And I explained that use of the data called how to handle censored data, and I explained a set of algorithms related to it. So my bottom line is once again that when you have few data points, and remember each of the data points may be tens of thousands of dollars because of the engineers, the equipment, and you often don't have time to repeat the experiments. So therefore, you have to extract the maximum amount of information that you can get from here. All right. So now you have a clean data, outliers have been removed. What do we discuss next? What we discuss next is to explain how to think about a good model for the data, or good hypothesis for the data. The first thing I mentioned was that most of the things that we have learned in classical statistics, those were sort of not wrong, but extremely limiting. Because what happens in those days, they didn't have computers. We are talking about 300 years ago. So they didn't have computers. The only thing they could handle were a few coin flip here and there and a few card tricks over here and there. And that's all they could do. And so they had only 1 or 2 little distributions that they could handle with. And all the statistics book, the thick, fat statistics books that you have is full of things that they could do because they didn't have a computer. But of course, the real world is very different. This is a tiny fraction of the distribution. The real distribution, there are so many other distributions that arises in physics that the statisticians, even the giants, could not really handle because they didn't have computers, they couldn't do it. So in that case, what I wanted to explain that the data analysis, modern data analysis, essentially liberates you from the people who were very sophisticated analytically, but really didn't have computers, so they couldn't really do much, and therefore could not really handle a vast amount of data that modern experiments produce. So this was my first point. That we should not be limited by what we learned in high school, because that's really was sort of not pre-1900. That's what was there. And so therefore, I explained that let's say you have a choice from this broad range of distribution functions that you think could be the possible hypothesis to explain the input data and connect the input data to the output data. And let's say you and your friend are sort of having a debate. Your friend is saying that, well, the data that you collected from the experiment, that data is best described by a Weibull distribution. Well, if you don't know what a Weibull distribution is, that's okay, because in the lecture you may remember that I discussed that in some detail. So do look over that thing. But let's say you are saying that no, it's log normal. And you are having a debate and you're having discussion. There are 8 points of the experimental points. And you fit it with your data distribution, and your friend fits it with his or her distribution. And they both look good. What do? And do you care that whether one is better than the other? The question is, you do care a great deal. Because in the lab, you may be able to test only a few of these things because it's so expensive. But let's say you have 10 wafers or 10 experimental samples that you can do it. But you will be selling hundreds of millions of these. In an iPhone, for example, the transistors will be hundreds and millions. And based on what you decide, what your distribution is, it is going to tell. So, for example, you see compared to previous one in this plot is the log. Time is plotted in a log, and this is the failure distribution, just plotted in a slightly different way. And all the fit that you did, everything looked good. You looked in here. But depending on who is correct, your friend on you, it is going to have dramatically different lifetime. You sell a product with this one, assuming that this is the distribution, then your company will go bankrupt because people will have customer as this IC return in a few months, whereas you may have predicted based on the little fit over here that everything will be fine. So therefore, it matters a great deal about what distribution you chose and whether the distribution is the correct distribution or not. And then in that case, the best way, and I'm not going to go through the details of this again because I did it already in the lecture. One of the best way you can fit the data is what I call the maximum likelihood method. This is something very important because the maximum likelihood method gives you the best, given the information about how they fail, that's the best possible fitting. And I explained to you, you did homeworks and all. I hope one thing that you never forget is that maximum likelihood method is the best way of fitting a data. And the straight line fit that you do in Excel and XYZ, well, those are sort of a poor man's version of this maximum likelihood approach. Second thing you do is that after you have fit the data, it's good to look at the data visually, because if your fitting is good, then the data should be arranged, the error should be arranged symmetrically around it, so that, sometimes it goes up, sometimes it goes low. But if it has a very systematic error means that whatever you fitted versus whatever the original data was, subtract the two, and then you look at the difference. And it turns out that if you do it this way, if you see something like that, something is wrong with the fitting. Although the fitting may look good, the error may be this and this may be comparable when you sum all the errors up, but actually this is saying that you are missing something systematic and you have to do better. And I explained several tests. One of them is Kolmogorov-Smirnov test. And in that case, what you do is you look at the one that has the maximum error. For example, in this one, maximum error, and see the number of points that you have and see whether that satisfied the Kolmogorov principle. So I explained a bunch of them, different techniques. I hope you will remember to first, anytime you have a hypothesis about F, remember the F which connects the input and output, that you sort of test through these various algorithms. Now it turns out that and I told you the story of Henrik Schon, who fabricated a huge amount of data and how he got caught, because sometimes when somebody's distribution looks too perfect, you can use the test that I just told you before to say that that person is actually committing a fraud. And it is very easy to catch this in these days, this type of thing. And that's why you may often see that many of the papers, especially in medical literature, is being withdrawn because the people manipulated the data in an incorrect way. I hope that you will never do that. The next point I wanted to make is that when, let's say you have two sets of data, and both of them are two hypotheses, yours and your friends, you ran all these tests and both of them are passing all of them because it's statistics, then the question is, which model should you take? And the answer is that this is the principle of parsimony, which says that whichever one can transmit information or describe a set of data with fewest possible parameters, well, that is the model you take for the printing, because anything that's simpler is likely to be more correct and more predictable. It's not a given rule, of course, things can be complicated, because what happens that as you increase the number of parameters, what happens, your data, your theory is going to sort of become more and more closer to the data that you have. But the thing is that if the fitting will contain now small information, small parameters, and then anytime you try to make a prediction, your prediction error will rapidly rise if you try to make overcomplicated model. So don't do that. And I explained what the principle is in terms of this, that the idea is that if you have some original data, and you want to send to your friend in Mars, the information about the data, then what you do is that you make a model out of it. You feed the data. Let's say you want to feed it by a straight line. Then you don't send the original data. What you send is the model coefficient. Let's say ax plus b. You send your friend a and b. Or if you have another model, ax squared plus bx plus c, then you send your friend a, b, and c. And then your friend receives it in Mars and tries to reconstruct the data. The fewer parameters you can send the data, and that leads to the smallest amount of error, is the model that it should be chosen. This is all in 1950s, as I explained, that people developed this technique, and this is widely used now. And I explained a few measures of, adjusted R-square, AIC, and BIC. These are different measures that balances the number of parameters you use in order to fit the data versus the number of data that you have. So using some of these things, none of them are guaranteed to work, but using some of these things will help you to stay from the abuses of excessive overfitting or data fitting, because sometimes if you want the data to fit in a particular way, you can throw more model parameters and it will fit better. But fitting doesn't mean there's a better model. This is a thing I emphasize repeatedly in the lecture. Finally, once the computers have come along, there have been a whole set of techniques. I told you about two, cross-validation method. What you should do is that when you have a bunch of points and you think this straight line is the right theory, then you should take a few points and fit a straight line. and then use the remaining data to see how well the straight line fits the remaining points. And you can take this training data from any of these combinations and use the other one as your prediction. And the idea is that way you would know that whether your straight line analysis is good or your a more complicated data would actually help. And you can do 1,000 of this in probably a few seconds in a computer. And therefore, this is a very powerful technique. Here you are sort of using the data itself to do the self-consistency check. If the whole thing is a straight line, then you don't fit everybody. You fit a subset of them and see whether the rest agree with you or not. And so these are computer-generated approaches that, of course, was not available before 1950s and 1960s. And so therefore, most textbooks don't really handle that. But very important, one line in MATLAB or in Excel, and it will completely transform the way you think about data. The other thing I approach is called the bootstrapping. And the bootstrapping method, you have a single sample. What you do, you copy the sample in many pieces and then randomly select from this many pieces. And even the single sample contains within it the information about the whole population. I explained that in great detail. But remember that there is this Blake's poetry to see the, see the universe in a drop of water or something like that, that if you know that although it's a single sample taken from a big population, or this is a population sample taken from within it, it knows about what type of range of information the population has. So you can use it repeatedly to tell the story of the population even when you don't know the population. So very important once again when you are trying to fit the data. So I will then move on and then tell you a little bit about how I said how to design experiments. That was the other set of topics. And in designing the experiment so that you have a good Y for a given set of X, what I explained to you that if you know the differential equation, for example, here we talked about bacteria, the stress-induced cell death. For example, if you raise the temperature, the bacteria die. And you can write an equation. What I said that if you just use this type of thing and do a simulation or do an experiment, then you have to do a lot of experiment. You have to start with saying different amount of bacteria. You have to say the rate at which they die. Different bacteria die at a different types of bacteria die at a different rate. And whether you, kept the temperature for 2 seconds or 2 minutes or 2 days. So you have to do hundreds of experiments in order to verify whether this theory is correct. The right way of doing it is not that. The right way of doing it is that as soon as you have an equation like that, then what you do is that you express them into a dimensionless form. And if you can express them in a dimensionless form, then it will dramatically reduce the number of experiments you do with no loss of information. And this is how all the planes are designed, wind tunnels are done, everything is scaled version of the big thing, and you always get things more or less right, because this is a very powerful approach, this approach of non-dimensionalization. And I explained, you did many examples using the Buckingham PI Theorem, Reynolds numbers, and all this other things I explained is based on this approach. So there's a way to, what is the bottom line? The bottom line is that there is a way to collect the variables in a way so that you have to do a fewer experiments. And what is the principle? The principle is that whether you're doing an experiment here or you're doing an experiment 1 galaxy away, the experiment should be the same. Answer, if it's physics, then the answer has to be same. And if the physics law cannot change, depending on where you did it. But 1 galaxy away, that person, those people may not measure things in the meter, second, and, in kilogram and all. They may have a different unit. So therefore, physics laws cannot have any unit to attach to it. Unit is a local thing. And all this thing does is sort of multiplies and divides in a way so that the parameters become dimensionless. And once the experiments are done in a dimensionless form, these are much more compact, much more informative. That's how these things are, that's why these things are very powerful. And I explained to you how if you then use those principles, you will realize that whether it's a plane, or whether it's a fly, or whether it is a bird, it turns out they all follow the same principle. And therefore, when you're doing an experiment, you should be really doing an experiment on the scaled variable, not the original variable, because that tells you the story about how when a body flies through the air, what is the drag and how the fundamental forces essentially gives rise to the flying shape that people have. So that's what I explained to you in that lecture. And finally, I explained to you that when you have many variables, how to reduce the number of experiments in many variables by Fisher's design of experiment principle. And for example, here we have 7 parameters, and even if you had just 2 levels, thin oxide, thick oxide, low doping, high doping, you'll have 2 to the power 7 experiments. Nobody will employ you in a company if you have to do 2 to the power 7 experiments to design this process, because it will take you a lifetime to do those experiments. It turns out there is a much more efficient way to reduce the number of experiments you do, and that's this Fisher's approach. And what Fisher is sort of a giant. Fisher is the quote-unquote Einstein of statistics. And what Fisher did was to tell the theorist and experimentalist to talk to a statistician before they do the experiment, so that the experiment these people do actually can benefit, can produce the maximum amount of information. And I explained to you how the Taguchi tables essentially allows you to do just a set of experiments. Instead of doing 2 to the power 17, you just do 8 experiments. And that may contain almost as much information. Similarly, 2 to the power 11 experiments, you do 12. So this is a dramatic reduction. This is not guaranteed. This is all statistics. But this tells you the principle through which you can actually reduce the number of experiments. And finally, I explained to you how you can use the analysis of variance, or ANOVA, in order to see whether the results that you're getting, whether a particular variable, for example, doping, actually has an effect or it doesn't have any effect. This is another way of reducing from that 7 variables. If it doesn't have any real, ANOVA tells you whether a variable has any effect or not. If it doesn't have it, then you can reduce it to 5, let's say. And then you can use various approaches like the Taguchi table in order to reduce the number of experiments. So I will not go through this because I spent a lot of time cleanly explaining how to think about the ANOVA approach. Finally, large data, right? That's a very big buzzword these days. And the first point I said that you should not be afraid of buzzwords, because there is often, there is not much to it, to these buzzwords, because many of these principles were actually known by 1930s and 1940s. It is just now we have computers, we have a lot of data, a lot of videos of cat videos and all. So therefore it has become commercially very relevant, but the concepts are very simple. The first thing I said was that when you have a large data, then in that case there is no physics of a human being, right? When you're trying to look at the picture of a various people, there's no physics model, so you have to do them statistically. And similarly, if you liked one book, you may have liked another book. That's the recommendation. And the thing is that, of course, you're a human being. You don't have, there's no physics model that tells you that you must like the other book if you like this book. So what they do is they classify. They try to see how similar are you with a bunch of other people. And once they know that you are sort of similar with other people, they try to say that, okay, this group of people on average like this book better or this movie better. You may like it too. So that's how they identify your friends. And since a person is known by the friends he or she keeps, So that is how this recommendation system works. And the important thing is that it has to be ultra fast, because you will be moving on to a new page in a second by clicking. So therefore, they have to show you the result. So sophistication is not necessary, but what is necessary is speed by which the recommendations are shown. So the most important one that has been known from early 19th century is this something called a principal component analysis. And what you do here is that when you have multidimensional data, for example, here gene 1, 2, and 3, or what you do is you project it on a two-dimensional plane using a known mathematical procedure called principal component analysis. I gave you very simple examples to understand it, and that immediately tells you that who is whose friend. For example, if you are here, they are going to make all this recommendation based on here. Not, this is a separate class. And so when somebody, your friend comes or somebody else comes, then they are going to make a recommendation based on this. Very simple approach, one line in MATLAB, slow, but it will give you all these principles. The important thing is that here I have shown in 3 axes, so therefore you can see the theta. But often there may be a million axes in here. So doing a fast two-dimensional projection to identify your friends is no mathematical. It's not complicated, but it is a computer science problem. And you can often use this technique. Another use is image transmission. Often, let's say you are reading New York Times, then or some other one where the picture previously they used to load line by line, and people got bored and they move on to the next page. These days, what they do, they will give the first approximation given by the first principal component, and give the outline of the picture, and then while you are looking at it or reading the text, the third, fourth, fifth component will come along, and that will hold you to that page. So this is again a very powerful technique that, in fact, as I explained, Netflix actually used it in its early days. The other approach people are using has to do with this deep network. And I said that deeper the network, shallower is your understanding. Physics, all they do is every line here, these are the input, and this is output. And you are trying to understand how a specific region, these are your friends. And you are trying to isolate your friends from the rest of the other people around you so that you can make a recommendation. And what the machine learning does is it just draws a bunch of straight lines. And then these straight lines are essentially just every line here is a straight line. And so if you need a couple of straight lines to isolate this point, that's all these nodes are. And I explained to you by very simple examples how the nodes work. So therefore, I hope you sort of will remember. And I also explained to you that many of these things which look mysterious, once you map it to the digital logic, all electrical engineers learn, you can see that really the nodes are actually and AND or NOT gates. And so therefore, there is nothing really very mysterious about how these networks evolve, and something that you may find interesting if you have done the homeworks. Finally, I said that in physics, don't use machine learning too often. People do that. People are trying to do that. Very dangerous. Because many times what will happen that it's a black box. So black box neural network. You have an input and you have an output. And if your physics problem, if you try to do it this way, it's like a Ptolemy's model. You have a lot of observation. Greek astronomers have done a lot of observation, and you are doing a Ptolemy model, which is a curve fitting. If you try to do that, what will happen that you cannot send a space probe to Mars or Saturn by Ptolemy's model. That's not possible because it's a curve fitting. Curve fitting works when you are recommending a book, because what is the worst thing that's going to happen? Your friend will not buy the book. But really what you need to do is to have a simple approximate physics model, idealized physics model, and fix the error or the difference with a machine learning network. That will be much more compact, much easily trained, And so therefore, bottom line, when you're doing physics, be careful. And I explained to you that there is different ways of doing it, and one important way of doing this physics-based machine learning is structural equation modeling. This is an old technique, but that at least gives you a physical idea. These nodes are then not straight lines approximation. These are actually physics-based nodes that an expert knows about, and use the expert to develop the network and then get the magnitude of the errors from a machine learning algorithm. So that's what you do. I also gave you an explanation, example of how people are doing the degradation of solar cells, for example, which is how solar cells lose power over the years. It's a very important technology problem, and how people are using the structured equation approach to capture some of these. This is not a blind use of machine learning. One has to be a little careful. So let me wrap up. I explained to you that in the beginning of the semester, the data is very important. Without data, there's no hypothesis, and without data, there is no technology. You have to measure things, and measure meaning data. And so therefore, from the very beginning, treat data with respect, and learning how to do it has been the cornerstone of the statistical research work for many years, almost 60, 70 years. How to keep the data as is and extract the story is trying to tell you. The second thing is I wanted to emphasize that you don't have to learn a lot of statistics to do this. In fact, it turns out that many software these days, even Excel, which looks very primitive in some way from the statistics, they have so many functions already embedded that if you just know what to use, and which I hope you know by now, you will be able to use just in a few clicks the most recent advances in statistics, if you just knew what to use. So I hope you have learned some of these, and these functions are always available, but you can flip through the slides I have explained in this. Next is the design of experiment. You must design experiment carefully, but carefully doesn't mean that you have to go and think a lot. It turns out there are very sophisticated algorithms like design of experiment, Taguchi design of experiments, scaling principles, Buckingham PI, that tells you exactly how you should be doing these experiments. And so therefore, there's no reason, again, all embedded in MATLAB. All you have to do is to know what to call, and it will immediately give you how you should design the experiments. So people generally learn it when they go to the industry, because then you cannot survive without learning this. But I hope you will learn it during graduate school also, because then that allows you to do your research much more efficiently and your simulation much more efficiently. And finally, I don't want to downplay the importance of machine learning. I mean, when it applies, it works like a magic. Of course, the book recommendation or a movie recommendation or the advertisement is raking in billions of dollars in profit for Amazon and for Netflix, for Google and all. But only thing I'm telling you that we are engineers, and engineers need to use it. We are not in the advertisement or classification industry. So therefore, when we do things for science and engineering, we have to borrow the tools that they have developed, but we have to be extremely careful and guided by physics and engineering principles before you do it. So we cannot really sort of put away all our physics books, all our statistics books, and simply use machine learning to do everything that we need to do. It doesn't work that way. Let me conclude then. This has been a great pleasure for me to teach this class. In the process of teaching the class, I had to sort of teach myself a lot of things. And I hope you enjoyed it. And if there are questions, you can always send me at alum@purdue.edu. and hopefully you will keep these notes next to on your desk, and from time to time flip through them and see whether you can use one or two or a few of the techniques that you learned in this course. So that's all I had. Thank you and good luck.